Come on. Oh, shh. Calculus. Hey, calculus. How's it going? How's it? That was nothing. We got stuff to do. Ain't nobody got time for that stuff. Them video games. Ain't nobody got time for that. We got Riemann sums to calculate again, but this time with a calculator. Oh, okay. Not a lot of time to waste on this. It's a pretty long one, but let's jump right into it. So for today, we're talking about Riemann sums yet again. Riemann sums very, very important to us here. They kind of lay the foundation work for what an integral is. So let's start off with example 1. It says sketch a graph, determine which Riemann sum will be an overestimate, and set up a Riemann sum using 4 equal subintervals. So what I did here is I went ahead and graphed 9 minus x squared. That's a upside down parabola. The negative tells me it's upside down. Squared tells me it's a parabola. 9 tells me it's shifted up 9. So here's what it looks like. And then it wants me to integrate from 0 to 3. So what I did is I went ahead and shaded in here from 0 to 3, as you can see there. And what I'm going to do real quick, while you're getting that finished up, I want to go ahead and draw the right-hand side of this. Say we just go from the x-axis up and from the y-axis right. So just draw the right-hand side of it real quick. This goes 9 up here. I'm just going to kind of make this a little bit bigger for us so you can really see what's going on. And I want to bust that thing up into 4 equal groups. Alright, I want to bust it up into 4 equal groups. Now, don't waste so much time with trying to figure out what these are. Just take 3, divide it by 4, right? This is how we came up with this, delta x in this case. You're going from 0 to 3, so 3 minus 0, and you want to use 4 subgroups, right? That means each subgroup needs to be 3/4 in width. So this is 3/4 plus another 3/4 will be 6/4, which is 3/2, plus another 3/4 will be 9/4. So don't waste time trying to do that by hand. Just use your little delta x thing. First minus the last divided by how many intervals you want. And what I need to do here is I need to set up a right-hand sum and a left-hand sum to try and figure out which one will be an overestimate, right? I've got a left hand, I've got a right hand, and I want to figure out which one will be an overestimate, and I want to prove it too. So I know I'm going to be divvying these things up. The question is it going to be, let me do this really lightly here, is it going to be a right-hand sum where the right-hand point touches? Or will it be a left-hand sum where the left-hand point touches? Well, you can tell right here the left hand is higher, but we'll get into that in a moment. So let's actually set up the sum here. L4, it's a left-hand sum of 4 subintervals. Remember, it's the delta x, 3/4, times, so for the left-hand sum here, we'll have all of your left-hand points. So we'll have f of 0 plus f of 3/4 plus f of 3/2 plus f of 9/4. So you take all your left-hand points and add up the y values. Now I have a handy-dandy calculator here, so I'm going to use it. Just for the sake of time, trust me on these. This one's going to take a while anyway. You plug a 0 in here, you're going to get 9. Plus, and if you want to go back and actually enter in 3/4 up here, you're welcome to do that. I'm just going to use a decimal approximation here. 8.4375. I want to be accurate to 3 decimal places, so I'm going to go out to 4 plus 6.75 plus 3.9375. Again, if I want to be accurate to 3 decimal places, which is the minimum requirement, then I want to go out to 4 in my calculations, which is 21.094. All right, and then the right-hand sum is going to be 3/4 times, and I use all of the right-hand points. So the easiest way that I like to do these is start from the left here on the left-hand sum and just go out 4 of your units: 0, 3/4, 3/2, 9/4. On the right hand, start with the right. So it's 3, 9/4, 3/2, and 3/4. So the only one I'm not doing there is 0. So I have f of 3 plus f of 9/4. That is a 9/4 right there. It doesn't look like it, but it is. Plus f of 3/2. Goodness gracious, I can't write this morning. F of 3/4. Alright, so f of 3 is 0 plus f of 9/4. Luckily, we've already done these. 3.9375 plus 6.75 plus 8.4375. And that is 14.344. So it's pretty easy to see the right-hand sum here is the one where the right-hand sum is the one where the right-hand point, this guy, is touching the graph. And that is definitely an underestimate. You're missing this little portion of the curve right where my pencil's at here. So right hand is definitely an underestimate, and left hand is definitely an overestimate. Alright. Now that's only for this case. Again, if this was something that was increasing, then it'd be the other way around. Alright. Alright. Down here on the bottom, it says the tables give the values of a function obtained from an experiment. Use them to estimate the integral from 0 to 6 f of x using 3 subintervals. 3 subintervals. Well, as soon as I see that little 3 subinterval thing, I'm going to say delta x, that's how wide your pieces are, should be 0 to 6. Right? So it's 6 minus 0, 3 subintervals, so divided by 3. So each little subinterval should be 2 units wide. So I'm going to kind of draw these out here, from 0 to 2, from 2 to 4, and from 4 to 6. So that's where my bars are at, right? 3 subintervals between 0 to 2, 2 to 4, and 4 to 6. And then it wants us to use the right endpoints for part A. So part A, this is going to be a right-hand Riemann sum using 3 subintervals. And what I do again is multiply delta x. Remember, this all came from yesterday, yes? This all came, I have it right here actually. All this comes from this guy right here. Delta x times all your function values added up. Okay, so delta x is 2 times, and I want the right endpoints. So start with the right. Here's an endpoint, here's an endpoint, here's an endpoint. So I need 6, 4, and 2. F of 6 plus f of 4 plus f of 2. And that is 2 times f of 6 is negative 10.5. F of 4 is 2.3. And f of 2 is 8.3. And through the magic of calculus, that's going to be 0.2. I did all these calculations beforehand just so we could speed up the video a little bit. B is a left endpoint. So a left endpoint using 3 subintervals is going to be delta x, which is 2. Now we're going to start on the left. So we have 0, 2, and 4. F of 0 plus f of 2 plus f of 4. F of 0, f of 2, f of 4. So that's going to be 2 times f of 0 is 9.3 plus f of 2 is 8.3 plus f of 4 is 2.3. And again, through the magic of calculus, 39.8. 39.8. I don't know where that came from. Part C. Your midpoint. That good midpoint. It's delta x, and I need all them good midpoints. All the middles. The 1, the 3, and the 5. It's f of 1 plus f of 3 plus f of 5. Which is 2 times 9 plus 6.5 plus negative 7.6. Oh, yes, yes, indeed, yes. And through the magic of calculus, it's 15.8. Yay! Okay, okay. Now, prepare yourselves, for we have our first real-life application of Riemann sums. Oh yes, this is going to be amazing. I hope you came prepared. Example number 3. Let's take some time to read, interpret, and extrapolate. Example number 3. The rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable and strictly increasing function r of time t. Ooh. The graph of r and a table of selected values of r of t for the time interval 0 to 90 minutes is shown above. Ooh, that's good stuff. So we've got rate of fuel consumption and time. Now, I'm going to tell you right now, the very first thing that popped out in my mind when I read this thing, this word right here, the rate of fuel consumption. That tells me this is a derivative of fuel because it's how fast fuel is being used. That tells me right off the bat, hey, this thing is a derivative of the number of gallons, the number of gallons of fuel. When you're given a rate gallons per minute, you have to understand that the rate is the rate of change, which is the derivative. So if I ever have to integrate it, like down here, I know what I'm going to be looking for is how many gallons are being used. But that's beside the point. We'll get to that in part D. So first off, it says that it is twice differentiable, and it's an increasing function r. It's strictly increasing all the time. That's going to be good to know. So anyway, this is the rate of fuel consumption. Now we are considering this as r of t. So it says, A says, use your data from the table to find an approximation for r prime of 45. Show the computations that lead to your answer and indicate units of measure. Okay, they're asking me for r prime of 45. R prime of 45. Well, there's a couple of things I want to point out real quick. R prime is the derivative of this, yes? It's going to be the rate at which these things are changing. So for 3a, what I'm looking for, r prime of t is going to be the slope of t. Or excuse me, the slope of r of t. R prime of t is the slope of r of t. Alright, so thinking about this here, r prime of 45, what they're asking me to find here, if you notice, I don't have 45 here. I'm going to go to my intermediate value theorem. And what I'm going to do is kind of use the slope of a secant line. Take the slope between, let's do this, r prime of 45, and it's going to be roughly equivalent, not equal, but it's going to be approximately r of 50 minus r of 40 divided by 50 minus 40. It's going to be your slope, y2 minus y1 over x2 minus x1. So I'm going to look up at my table there. R of 50 is 55 minus R of 40 is 40. 50 and then 50 minus 40 is 10, obviously. So what we end up with here, we've got 55 minus 40. So that's going to be, what, 15 over 10? Which is going to leave us with roughly 1.5, and just for the sake of consistency, 3 decimal places, 0, 0. And that is how many gallons are being used every minute, but we're integrating here, right? Or excuse me, we're differentiating. So this is the rate of gallons per minute. So this is going to be gallons per minute squared. All right? Kind of think about this, if this is gallons per minute, if that was kind of like velocity, feet per second, you only have one unit of each, feet and second. The derivative of that, which is acceleration, is feet per second squared. So it's that same concept there. All right. Part B says the rate of fuel consumption is increasing fastest at time equals 45. What is the value of r prime of double prime of 45? Increasing fastest is the key word there. This is an AP style question in case you hadn't noticed. Increasing fastest is the key word there. At 45, so 40, 50, 60, so 45 is right here. You're increasing the fastest, and it wants to know what's going to happen at r double prime of 45. Well, if r prime is your derivative, right? R prime is the rate of fuel consumption of r of t. Since r prime is the greatest, the rate of fuel consumption is the greatest, is increasing fastest, that means that your slope is greatest here. That means r prime is going to be greatest there. That means that r prime has a maximum right here. Think about that for a second. If r is increasing the fastest at this point, that means that r prime is going to have a maximum value. The slope of this graph is going to have a maximum right here. This is your maximum slope. So here's how I'm going to say this. Let's go over here. I'm going to write down r prime of t is going to be the rate of the fuel consumption of r of t. So it's the rate of r of t, right? R prime of t is the rate of r of t. Now, since r of t is increasing fastest at t equals 45, then r prime of t has a, we can call this a local maximum. It has a local max at 45, right? Now, I want you to think about this. If your derivative has a maximum at 45, what is r double prime going to look like? What is r double prime going to look like right here? What is the slope of this maximum? Well, it's going to be 0. So here's what we're going to say. The question actually stated that it is twice differentiable, right? I'm going to use that in this example, or in this explanation. I'm going to say since r of t is twice differentiable, then r double prime of 45 must equal 0. What that means, since I am increasing fastest, r prime has a maximum. And the derivative at a maximum is always 0. So at 45 you have a maximum. And that maximum is going to cause r double prime to be 0. Okay? Alright, let's finish this up here. Part C, I'm going to flip back over. Part C says to approximate the value of the integral from 0 to 90 of r of t dt using a left Riemann sum with the 5 subintervals indicated in the data table. So here's your intervals up here. And is it going to be less or greater than the original? Alright, so from 0 to 90, I'm going to use 5 subintervals, and they're going to be left Riemann sum. So let's see, 1, 2, 3, 4, 5. So I've got a little block here, a little block here, a block here, a block here, a block here. From 0 to 30. From 30 to 40. Notice that these values are given in my table, or in my thing here. Like this. I'm using a left sum, so all the left sides are going to be touching. 0 to 50. 50 to 7 da. And 70 to 90. So the only point that I'm not going to use here is going to be 90, it looks like. Now if you notice, those intervals are not evenly spaced. And that's okay. That is alright. So I've got this table over here on the other side of me, so I'm going to flip this over here. For 3C, my left Riemann sum using 5 subintervals. Alright? And really, all I'm going to do is take the area of each one of these rectangles. My delta x is not staying the same here. So I'm just going to take the area of all the rectangles. So it's 20 times 30 plus 30 times 10 plus 40 times 10, 55 times 20, 65 times 20. This is the height and the width of each one of the rectangles. Alright, so let me flip this over. If you want to pause that, pause it real quick, get those. Alright, so again, it's 20, right? 20 by 30, 30 by 10, 40 by 10, 55 by 20. Notice these points are all given here. Alright, I'm using all my y values, and then my last one here is 65, and that one is 20 units long. So I'm finding the area, just multiplying and adding up all the rectangles. And it happens to be 3,700. Now, is this going to be an over approximation or an under approximation? Well, it's obviously under. Look at it. You're missing all these bits here. And that has to deal with the strictly increasing. Since you're strictly increasing using a left Riemann sum, this Riemann sum I misspelt Riemann. It's R-I-E, excuse that. This Riemann approximation is less than the actual value and that is because R of t is strictly increasing. Messy handwriting. Okay, I'm trying to wrap this up before the 30-minute mark. I apologize for the length again, but last question, and this one is an awesome question. D says, for 0 to 90 minutes, explain the meaning of the integral from 0 to b in terms of fuel consumption for the plane. The integral from 0 to b of r of t dt. What does this mean? Well, like I said before, if r of t is the rate at which fuel is consumed, it's the gallons per minute, then the integral of that has got to be the total gallons of fuel used from t equals 0 to t equals b minutes. So back up here on part C, where I have my 3,700, what this is talking about is gallons of fuel. And then the last question here says, explain the meaning of 1 over b of the integral. What happens if you take the integral and divide it by b? Well, what does b represent? B represents the number of minutes. So if you take how long you've been running the plane and divide it by the number of minutes, that's going to be your average gallons used every minute. You're finding an average here. 1 over b, integral from 0 to b of r of t dt. That's going to represent the average gallons every minute. Average gallons used per minute. And if you're reading the integral, it goes obviously from t equals 0 to t equals b. I know it's a lot of information, but Riemann sums kind of lay the foundation for the last third of calculus. So keep these in mind as we go into this thing. The application obviously took a little bit longer than actual Riemann sums. We'll talk more about this when we get to class.